During the last few weeks, we've spent a lot of time learning how to apply various derivative shortcut techniques. We know how to compute derivatives of many types of functions, but the focus of Chapter 4 is really on how we use the derivative. So Section 4.1 is entitled Using the First and the Second Derivative, and the goal of the section is to be able to use these quantities to determine the high and low points on the graph of a function. For example, in this video, we're actually going to look at a simple cubic function, x to the third minus 3x squared plus 2x, and we're going to learn how to compute the exact high point right here and the exact low point right there. And those points have names. We call them local maxima and local minima. So that we say that a function is a local maximum if at a, if f of a is greater than or equal to f of x for x values close by. We say that a function has a local minimum at a if f of a is less than or equal to f of x for x values close to a. Another way of phrasing this is that the outputs at a are greater than the outputs nearby for a local maximum. The outputs at a, the output at a is less than or equal to the outputs at points nearby for a local minimum. So for example, in this graph, we have a point right about here that appears to be a local maximum because the output there is greater than the outputs nearby. In other words, the function is at its highest here. There seems to be a point right around 1.5 where the function has a local minimum because the output at that point is less than or equal to the outputs of points nearby. In this case, the function has one local maximum and one local minimum, but all sorts of things can happen. A function can have 5, 10, however many local maxima and local minima. So the first step in computing local maxima and local minima is to look at what we call critical points. A critical point of a function is a point in the domain of the function where either the derivative is undefined or equals 0. For example, and I should point out that critical points are going to be candidates for local maxima and local minima, but a critical point doesn't have to be either. So for example, in the previous picture, we have a critical point right around here where the derivative is 0. We have a critical point right around here where the derivative is 0. This is a maximum or this is a minimum. In this case, each critical point is either a maximum or a minimum, but that doesn't always have to be the case. For example, f of x equals x to the third. Its derivative is 3x squared, which is equal to 0 at the origin. All that tells me is that the slope of this function is 0 at the origin. It's kind of hard to tell from my graph, but the graph actually is flat at the origin. So in this case, 0 is a critical point, but it's neither a local max nor a local min, which we can see. So I like to think of the critical points as being candidates for local maxima or local minima, but they're only candidates. So how do we find critical points? Well, if we want to find critical points where the derivative is undefined, we look at the graph of the function and we look at for cusp or sharp corners. For example, the absolute value function has a sharp corner at the origin where the derivative is undefined. So the origin, x equals 0, would be a critical point for this function. Now to find where the derivative is 0, which is what we'll be doing most of the time, the process is as follows. We compute the derivative of the function, which we're pretty adept at now because we've been looking at shortcut rules in all of Chapter 3. We set the derivative result to 0 and then we solve for x. And this process of solving may require factoring, the quadratic formula, logs, trig functions, all sorts of things. There's no set rule. So let's go back and take a look at this cubic function, x to the third minus 3x squared. We can see that there's going to be a critical point right around here and a critical point right around there. We're going to find those critical points exactly. So we first compute the derivative, which by the power rule is 3x squared minus 6x plus 2. And we know at this point and at that point the derivative or the slope has to be 0. So we take this derivative formula and we set it to 0. 3x squared minus 6x plus 2. In this case, we have a quadratic. And any quadratic can be solved using factoring or using the quadratic formula. I'm going to use the quadratic formula in this case, so x would be minus b plus or minus the square root of b squared, which is 36, minus 4a, a is 3, times c, which is 2, all divided by 2 times a, and 2 times a is 6. So this gives us 6 plus or minus, the quantity under the square root will be 36 minus 24, which is 12, all divided by 6. This radical can be simplified. The square root of 12 can be, we can simplify this radical, it's 2 times the square root of 3. We can break this up into 2 across the denominator, so we have 6 over 6, which is 1, plus or minus 2 over 6, which is 1/3 times root 3. So the exact critical points, and we want exact critical points, are 1 plus or minus root 3 over 3, which is 0.422, approximately 1.577. Now, the techniques for determining whether these candidates are actually maxima or minima come down to 2, which are algebraic in nature. We can tell from the graph of the function that the 0.422, which is right around here, is going to be a local maximum, and the other one is going to be a local minimum. But the next two tools we're going to talk about are algebraic, which means they don't require the graphs. So let's take a look at the first derivative. But before we do that, we need to recall an important fact about the derivative, and that is the sign of the derivative, whether it's positive or negative, tells us whether the function f is increasing or decreasing. The sign of the second derivative will tell us something about concavity. We'll come back to the second bullet in a moment. Okay, so here are our critical values. 1 minus root 3 over 3, which is about 0.422, and 1 plus root 3 over 3, which is about 1.577. These are points where the derivative function is 0. So the graph of the derivative function would have to cross the horizontal axis here and there. Now, this type of picture is what's known as a sign chart. And here's what we're going to do. We're going to look at the derivative, and we're going to choose values within each of these zones and plug them into the derivative formula. Now, it doesn't matter what you choose. I'm going to choose values that are convenient and easy to plug in the derivative. So first, I'm going to choose a value of x somewhere to the left of 0.422. Any value would work. 0 is a very convenient value. If I plug 0 into this formula, I get 2, which is positive. Here's what that tells me. That tells me that everywhere to the left of this number, the derivative is positive. And if the derivative is positive, the function would have to be increasing, the original function. Let's choose a convenient value in here, something between these two values. 1 would be convenient. So let's plug 1 into the derivative formula. If we plug 1 in here, it will simplify to be minus 1, which is negative. That says that the derivative is negative throughout this zone, so to speak. And if the derivative is negative, the function would have to be decreasing. Let's choose something in the last zone, so to speak, something to the right of the 1.577. Let's choose 2. If we take 2 and plug it into our derivative formula, it will give us 2, which is positive. So, to summarize, the derivative is positive here, always positive. The derivative graph would always be negative here, and the derivative graph would always be positive. That means the function is increasing here, and then it's decreasing throughout this zone, and then it switches from decreasing to increasing up again. And so that allows us to ascertain each critical point insofar as whether it's a maximum or minimum. Let's summarize that. The function f switches from increasing to decreasing at 1 minus root 3 over 3, so it is a local maximum. The function f switches from decreasing to increasing at 1 plus root 3 over 3, so it is a local minimum. Now again, this process of using the critical points to divide the number line up into zones and choosing a test value within each zone is known as a sign chart. This is known as the first derivative test. Suppose that you have a critical point at x equals a where the derivative is 0. If the derivative switches from positive to negative, then the function has a local maximum there. If the derivative switches from negative to positive, the function has a local minimum there. If the derivative does not change signs, then the function has neither a local maximum or a local minimum. And a sign chart using test values helps when applying this test. Now let's go back to the second point regarding the second derivative. The sign of the second derivative yields information about the concavity. For example, if the second derivative is positive, that means the graph of f is concave up at that point. If the second derivative is negative at a point, that means the graph of f is concave down. So our original function had a derivative that was equal to 3x squared minus 6x plus 2. Let's take the second derivative of that quantity. If we do so, we get 6x minus 6. Let's take our first critical value, 1 plus root 3 over 3, which is about 1.577, and plug it into the second derivative. If we do that, we get 3.462, which is positive. Likewise, if we take our other critical value, let me back up a second. Since this is positive, this 3.462, since that's positive, we know that the function is concave up at this critical point. Because the function is concave up, that critical point has to be a local minimum. Now let's take a look at the other critical point. The other critical point was at 1 minus root 3 over 3, which is about 0.422. If I plug that into the second derivative, I get about minus 3.464, which is less than 0. That tells me that at that critical point, the function is concave down, which means the function has to have a local maximum there. And this is what we call the second derivative test. The second derivative test for classifying critical points as local maxima or local minima. Suppose that x equals a critical point of f where the derivative is 0. Plug that point into the second derivative. If the result is negative, then the function is concave down there, so the x equals a is a local maximum. If the second derivative is positive there, that means the function is concave up, which means we have a local minimum. If the second derivative is equal to 0 at our critical point, the test is inconclusive. All sorts of things can happen. You could have a maximum, a minimum, or neither, so you just have to try something else. Okay, the second derivative has another use. We know that when the second derivative is positive, the function is concave up. We know that when the second derivative is negative, the function is concave down. So a point where the function switches concavity is what we call a point of inflection. So here, f double prime is positive. Over here, f double prime is negative. So where the function switches concavity, which is what we call a point of inflection, is where the second derivative is equal to 0. A point of inflection of the function is a point in the domain where the second derivative changes from positive to negative or vice versa. To find a point of inflection, we compute f double prime of x, set the result to 0, and solve for x. In the case of our function, f double prime of x is minus 6 plus 6x. We set that to 0, and we get x equals 1. That is our point of inflection. So let's go back and take a look at the graph. The point of inflection was at 1. We had a local maximum at 1 minus root 3 over 3. And we had a local minimum at exactly 1 plus root 3 over 3. So what I would like for you to do in preparation for class is I would like for you to look at a somewhat similar cubic, x to the third plus 3x squared minus 6x minus 3. I would like for you to find the exact critical points that may require using the quadratic formula for this example, because when we take the derivative and set it to 0, we'll have a quadratic. Classify each critical point as a local maximum or minimum using the first derivative test. That is, make a sign chart just like earlier in this video, and then also classify each critical point as a local maximum or minimum using the second derivative test. So the first derivative test and the second derivative test are separate means for classifying a critical value, a critical point, as a maximum or minimum. And then lastly, find the points of inflection by computing the second derivative and setting it equal to 0 and solving for x. I'll see you in class.